Example 5, use a graph to give a rough estimate of the area of the region that lies beneath the curve y equals cube root of x versus 0 to 8, then find this exact area. So if I get my calculator out, maybe, there we go, and type in my equation, the cube root of x, the cube root button is in the math menu, number 4, and then x, that's how you enter that, so hit math. And then 4, give it the cube root up there. And we just want to evaluate it from 0 to 8. If I just get like at each integer value, so 0, 1, 2, 3, 4, 5, 6, 7, 8. I can get, well, I put 56, hang on. 5, 6, 7, 8. There we go. So that's every integer value. You can see the lowest number is 0, the highest number is 2, everything else is in between 0 and 2. And if I go to my graph paper that I've created over here, and let's see, maybe a way to do this here, let's move this over here. Excellent. So I plot those points. I got 0, 0, 1, 1, 2, 1.26, 3, 1.44, 4, 1.59, 5, 1.71, 6, 1.81, 7, 1.91, 8, 2. Just a nice steady increase like so. And there's our graph. Alright, so what we've learned about these problems is that the answer to this problem, which is the integral of the cube root of x dx from 0 to 8, is equal to the area under the curve. So if I were to put a vertical line right here and kind of shade it in like so, the area of that region is the answer to that integral. So those match each other. I did a 1-to-1 scale here, which means that every one of the boxes that are here is going to have an area of 1, right? 1 unit right, 1 unit up, so this box right here, if I just highlight that one box there, the area of that box is 1 square unit, right? We all buy that? If we scale it differently, like let's say I said 0.25 and 0.25, every one of those boxes is 0.25 by 0.25, so 1/16 would be the area of each one individually. So if you're going to estimate using the area of the boxes, a 1-to-1 scale is easier to do, but you can do it with anything you want. So basically what I want to do here to estimate the area with this is just figure out how many full boxes I have. So if we take a look, we got 1, 2, 3, 4, 5, 6, 7 for sure full boxes, right? This is almost a full box. I'm going to go ahead and count that as a full box too. 8. Again, we're estimating so we have a little bit of freedom to do stuff like this. If I were to pair these guys up here, use some different colors, I'm going to say this guy here and this guy here together, that and that kind of make up one full box, right? This little bit here fills in the gap there. And similarly for this one here and this one here, and also this one here and this one here. I'd say each of those makes about a full one each, maybe a little bit more, a little bit less, but again, we're estimating, so we have some freedom. And then this is about a half a box here, right? So if we count them all up, 1, 2, 3, 4, 5, 6, 7, 8 full boxes, 9, 10, 11, and about a half. That'd be my guess, 11 halves. So approximately 11 halves units squared. And again, that's not using any calculus whatsoever. I just graphed it and I estimated, I ballparked things. I used a little geometry, a little eyesight, nothing, no major math going on here. All right, so once I've estimated it using the graph, now I want to go ahead and use calculus to get the exact answer. And I'm expecting something around 11 halves. What am I thinking? Hold on. You guys need to correct me when I mess up like this. 11 and a half. So 23 halves, sorry about that. So obviously there's major enough math that we don't want to make calculation errors in our writing our answer. But 11 and a half is what we got for the answer. So I would expect the answer to this to be somewhere around 23 halves. 11 to 12, somewhere in there. I don't know what the exact answer is, but I should get something close to that, because again, that's what estimates are all about. We're not about perfection, we're about getting close so that when we get the actual answer using a good technique, then we can be sure that that answer looks reasonable based on what it should be. So if I'm doing now this problem here, just the antiderivative, first thing I would want to do is create a structure that's easier to use, which is x to the 1/3 power, like so. And the antiderivative of x to the 1/3 power is going to be x to the 4/3 power divided by 4/3, which is the same as times 3/4. We're supposed to be going from 0 to 8, which again, based on the fundamental theorem of integral calculus that we learned yesterday, it simply means to put 8 in for x and then put 0 in for x and subtract the two results. So I'm going to get 3 times 8 to the 4/3 power over 4 minus 3 times 0 to the 4/3 power divided by 4. That equals 0, so it's irrelevant. To do 4/3, 8 to the 4/3, we take the cube root of 8, which is 2, 2 to the 4th is 16, so we get 3 times 16 over 4, which is 48 over 4, which comes out to 12. So the exact answer is 12. We got 11.5, which I buy that. So correct answer, the exact area, is that. This is the approximate. So if they do ask you to graph it, use that as an approximation to get the exact answer, then that's what I'm looking for. Show me the graph, show me where you figured out what the area was. I can believe you can count. So I mean, the fact that I doctored this up with check marks and scribbles and stuff, I believe you have the ability to put your finger on your graph paper and 1, 2, 3, count. You don't have to mark it up for me to believe you counted the boxes. But again, a 1-to-1 scale is nice. If you'd gone with if we did a half and a half, each one of the boxes is a quarter, that would have given us a little more accuracy, but it would have given a heck of a lot more boxes to count too. So, you know, the whole idea of estimation is that we want to get close. There was enough precision there to get close with the 1-to-1 scale. You know, just a thought, if you go with a smaller scale, you can get a more accurate approximation. I want to go back there. So again, 12 is the exact answer, and that's what we're